A classical n-dimensional image is a dense grid of discrete numerical values. Every pixel occupies its own localized position in memory. Quantum image processing replaces that architecture by encoding the entire classical grid into the amplitudes of a single, normalized quantum state vector. Because the data exists in a state of quantum superposition, we can apply analytical operations across every pixel in the image simultaneously. Loading high-resolution data creates an immediate bottleneck. Initializing this specific state vector requires an exceptionally deep quantum logic circuit. Deep circuits require time, which is the exact resource we lack. Current quantum computers operate on noisy intermediate-scale quantum hardware. NISQ hardware operates under strict limits. Qubits suffer from short decoherence times, and gates have high error rates. Standard state preparation protocols, like the flexible representation of quantum images, require a gate complexity of O(n)². If you double the pixels, you quadruple the length of the initialization circuit. This quadratic scaling presents a hard physical barrier. If we load high-resolution scientific data, the quantum state will succumb to environmental noise and decohere long before the circuit finishes. The field of quantum image processing currently relies on several competing color encoding formats, such as FRQI, NEQR, and MCRQI. QPIXL framework provides a uniform mathematical architecture that overarches all of these disparate models. Now it functions as a modular engine. Instead of treating each format as a separate physical problem, QPIXL isolates and optimizes the underlying color encoding unitaries they all share. By restructuring the math, QPIXL reduces the gate complexity from O(n)² to the theoretical minimum of O(n). The circuit depth scales linearly with the total number of pixels. It achieves this linear scaling without relying on extra error-prone ancilla qubits to store intermediate data. QPIX reframes quantum state preparation, shifting the burden from hardware brute force to algorithmic optimization. To see why traditional scaling fails, consider a 2x2 image. Its block diagonal matrix shows 4 isolated RY rotations. Standard methodology uses multi-controlled logic gates. Since hardware cannot natively execute these, they fracture into basic single-qubit and CNOT gates. Encoding 4 pixels takes 74 inefficient operations. As the image scales, every additional control qubit geometrically multiplies the required number of elementary gates. The operational risk lies specifically in the CNOT gates. Because they entangle 2 separate qubits, they generate significantly more noise than single-qubit operations. Stacking thousands of noisy CNOTs on a NISQ device compounds those errors, guaranteeing total state vector collapse before the encoding phase can finish. Pixel-by-pixel multi-controlled gate decomposition physically prevents high-resolution quantum image processing. QPIXL bypasses multi-controlled gates entirely, deploying a repeating sequence of uniformly controlled RY rotations. The physical circuit maintains an alternating 1-qubit and 2-qubit rhythm. Rather than targeting individual pixels, the CNOT gates systematically permute the 2x2 blocks based on control qubit parity. This rhythm requires calculating a new vector of hardware angles, theta hat, to ensure the sequence matches the original image data. Finding theta hat requires mapping the target pixel angles through a highly structured linear system. First, the system applies a gray code permutation. This sorts the binary pixel positions into a sequence where only one bit changes at a time, aligning with the alternating CNOT structure. Next, the permuted vector is processed through a scaled Walsh-Hadamard transform. The output of this system is the exact coefficient vector dictating the hardware angles for an O of n depth circuit. Returning to our 2x2 baseline, the 74-gate Barenko circuit is replaced by a QPIXL architecture, requiring exactly 4 RY gates and 4 CNOT gates. Mapping image data through the transform domain bypasses the geometric penalty inherent in multi-controlled hardware gates. The Walsh-Hadamard transform provides a mathematical basis for direct post-synthesis circuit compression. In a synthesized quantum circuit, randomly deleting native gates breaks the logic and mathematically corrupts the global state vector. QPIXL bypasses this by applying a magnitude thresholding criterion directly to the theta hat coefficients while they are in the transform domain. The algorithm isolates the least significant hardware angles and forces them to exactly 0. An RY gate with a rotation angle of 0 does not alter the state. It acts purely as an identity matrix and is deleted. With the zeroed RY gates deleted, the surrounding identical CNOT gates slide together along the wire. Because they share a control qubit, they undergo parity annihilation, physically canceling each other out. Because this thresholding occurs in the transform domain, we trigger physical CNOT annihilation to shrink the circuit depth while preserving the known local correlations of the original image. We validate this theory using heavy scientific datasets, like those generated at synchrotron light sources. Our test dataset is a 256 by 256 pixel micro-CT scan of a ceramic matrix composite used to track material deformation. This dashboard tracks the baseline metrics. Preparing this image requires 17 qubits and an uncompressed ON circuit containing 65,536 elementary gates. Applying a 75% compression threshold forces the majority of coefficients to zero, yet the visual retention of the macroscopic composite fibers remains intact. Inside the hardware, the resulting CNOT annihilation cascade drops the physical gate depth by over 61%. Pushing the model to 90% compression maintains recognizable structure while dropping the requirement from 65,000 gates down to under 7,000. QPIXL's strict linear architecture and transform domain pruning provide an algorithmic bridge to transition heavy n-dimensional data into near-term quantum hardware.